Let's now discuss the appropriate fitting. So just for context, we started the conversation about a scenario where the model is underfitting. This is illustrating this with synthetic artificial data points with a scenario with two classes or two categories. Underfitting is where you see that the estimation or prediction of the model is a frontier or boundary dividing the data points. So here that boundary is overly simplistic. We talk about the other scenario, which is the other extreme, which is a scenario in which the boundary is one such, like you can see how I'm moving the cursor here, is one where the model is basically memorizing based on the training data subset, memorizing very details, the levels of sophistication relative that are only pertinent to the training data set, but the model fails to make generalizations with unseen data. Okay, and so the scenario we're talking about now is one scenario in which, again, the data points are represented here with two shapes. The estimation or the model prediction is a curve. There's the boundary or frontier, and what we see in this outcome is most of the points to the left are classified with one shape that tends to be star. There is a handful of mistakes. Basically, there are two circles there on the left, and then most of the points on the right are circles, and there is a handful, one star over there. So this is precisely in the spirit of being a balanced situation. So we would like to have machine learning models that somehow are performing in the extremes between underfitting and overfitting. You kind of need to have a compromise in whatever metric we're using for quantification of model performance, how the model is performing in the training data subset. We would like to perhaps pay less attention to the noise in the data subset and maybe have more of an effort in patterns that can be generalizable, right? This will definitely contribute in having a model that makes successful predictions in future unseen data samples. That's kind of like the end goal. So another important thing to keep in mind is that the validation data subset could be useful for building models on the training data subset and validating them with the validation data subset. It can also be useful for monitoring performance, specifically quantification of model performance. We can also aim for a model that performs good enough, in a sense, with both the training data and the validation data, and would like to capture a model that gives the best validation performance. Some machine learning techniques and algorithms that can be used to find appropriate fit models are techniques that include, for example, early stopping. This is when you train a machine learning model with various iterations, and you are keeping track of the model performance for each iteration. And so in a sense, it's kind of converging to an acceptable model performance from these iterations. Another technique is regularization, which refers to a broad range of techniques for forcing the model to be artificially simpler. And one more method belongs to a family that's called ensembling family of methods. These ensembles are machine learning methods that combine predictions from multiple separate models.